a guide to establishing a colony in space. As humanity ventures further into the cosmos, the idea of establishing colonies in space has transitioned from the realm of science fiction to a tangible and exciting possibility. The concept of creating human habitats beyond Earth is not only a testament to our insatiable curiosity, but also a potential solution to challenges such as overpopulation, resource scarcity, and the long-term survival of our species. In this comprehensive guide, we will explore the fascinating journey of establishing a colony in space, covering everything from the initial concept to the intricate details of life in outer space, understanding the need for space colonization. Establishing a space colony beyond Earth is crucial for humanity's survival and progress. It serves as a backup plan, safeguarding against planetary threats like asteroids or environmental collapse. Additionally, it opens new frontiers for exploration, offering a unique chance to study extraterrestrial environments and potentially discover life beyond our planet. A space colony fosters technological innovation, pushing the boundaries of human achievement from sustainable life support systems to advanced resource utilization. It's not just a necessity, it's an opportunity to redefine what's possible, inspiring generations with the prospect of a thriving, self-sustaining human presence beyond the confines of Earth. Before delving into the intricacies of building a space colony, it's crucial to grasp why such an endeavor is necessary. Earth, despite its vastness, is a finite resource, and our population continues to grow. The challenges of climate change, depletion of natural resources, and the ever-looming threat of global catastrophes make the prospect of establishing a colony beyond our home planet increasingly appealing. Furthermore, space colonies offer a unique opportunity to diversify human existence, allowing us to spread our wings beyond the confines of a single planetary body. By creating self-sustaining habitats in space, we can mitigate the risk of extinction events on Earth and ensure the long-term survival of our species. The blueprint: choosing a location. Selecting the right location for a space colony is paramount to its success. The Moon and Mars emerge as the most viable candidates for human habitation due to their proximity to Earth and the presence of essential resources. The Moon, with its relatively short distance from Earth, can serve as a stepping stone for deeper space exploration. Mars, on the other hand, offers a more Earth-like environment with a day-night cycle and the potential for terraforming. Once the location is determined, the next step is to design the colony's structure and layout. The architecture of a space colony must account for factors such as radiation exposure, microgravity effects on the human body, and the need for artificial gravity to maintain health. Building the infrastructure. Constructing a space colony requires a combination of cutting-edge technology and innovative engineering. The colony's infrastructure must provide a life support system, shielding inhabitants from the harsh conditions of space. Solar panels or other sustainable energy sources are vital for powering the colony, ensuring a constant supply of electricity for life support, communication, and research activities. The construction process may involve assembling modular components in space, utilizing robotics, and employing 3D printing technology for on-site fabrication. The modular approach allows for flexibility in design, scalability, and easier transportation of materials from Earth to the colony site will be needed until the colony is self-sustaining. Living in space presents numerous challenges that require creative solutions. Microgravity, for example, affects the human body, leading to bone density loss and muscle atrophy. To counteract these effects, space colonies may incorporate rotating habitats to simulate gravity artificially. Additionally, life support systems must efficiently recycle air, water, and waste to maintain a closed-loop environment. Hydroponic and aeroponic systems could be employed for growing food, reducing the dependency on Earth for sustenance. Innovations in biotechnology and genetic engineering may also play a role in enhancing human adaptability to the space environment. Living on another planet, challenges, and more. Living long-term on another planet, such as Mars, for example, poses numerous challenges for astronauts, both physiological and psychological. Here are 5 of the top challenges Mars explorers will face. Radiation exposure. Mars lacks a thick atmosphere and a strong magnetic field, which means that the surface is exposed to higher levels of cosmic and solar radiation compared to Earth. Long-term exposure to such radiation can increase the risk of cancer and other health issues. Astronauts will need effective shielding or underground habitats to mitigate this risk. Microgravity effects. While Mars has only about 38 of Earth's gravity, it still presents challenges associated with microgravity. Prolonged exposure to low gravity can lead to muscle atrophy, bone density loss, and cardiovascular issues. Astronauts will need to engage in regular exercise and possibly employ artificial gravity solutions to counteract these effects. Isolation and psychological stress. Living on Mars would mean isolation from Earth and confinement within a limited space for extended periods. This isolation, combined with the challenges of living in a harsh environment, can lead to psychological stress, anxiety, and other mental health issues. Mission planners will need to address these concerns through psychological support systems, regular communication with Earth, and recreational activities. Limited resources and self-sustainability. Mars is an inhospitable environment with minimal resources. Astronauts will need to rely on a closed-loop life support system for air, water, and food. Developing sustainable systems for resource utilization, waste recycling, and food production will be crucial for long-term habitation. Communication delay. The distance between Earth and Mars varies, and the time it takes for signals to travel between the two planets can range from a few minutes to over 20 minutes. This communication delay can pose challenges in emergency situations and may affect the ability to make real-time decisions. Astronauts will need to be trained to handle situations autonomously and with minimal guidance from mission control. Addressing these challenges requires a multidisciplinary approach involving advancements in technology, medicine, psychology, and sustainable living systems. Ongoing research and development are essential to ensure the safety and well-being of astronauts during extended missions to Mars. Eating on another planet. Food supply for a planetary space colony. Creating a sustainable food supply on a planet like Mars, for example, is a critical aspect of long-term human habitation. Since Mars has a harsh environment with extreme temperatures, thin atmosphere, and poor soil conditions, astronauts would need innovative solutions to grow their own food. Here are some potential methods. Hydroponics and aeroponics. Traditional soil-based agriculture may be challenging on Mars due to poor soil quality. Hydroponics and aeroponics are soilless cultivation methods that use nutrient-rich water or a mist environment to deliver essential nutrients directly to plant roots. These methods can be adapted for use in controlled indoor environments, providing a more controlled and efficient way to grow crops. Bioregenerative life support systems. Bioregenerative life support systems involve creating a closed-loop ecosystem where plants, microbes, and other organisms work together to recycle waste products and produce oxygen and food. Waste from human activities can be used as fertilizer for plants, and plants, in turn, release oxygen. This approach mimics a natural ecosystem and can contribute to long-term sustainability. Martian greenhouses. Greenhouses can provide a controlled environment for plant growth, protecting crops from the harsh Martian conditions. They would need to be equipped with temperature control, artificial lighting to compensate for the limited sunlight on Mars, and a water supply system. Greenhouses could be constructed using lightweight, durable materials, and their design would need to consider the unique challenges of Mars. Genetic engineering and adaptation. Scientists could explore genetic modification of crops to make them more resilient and adaptable to the Martian environment. This might involve altering plants to withstand lower gravity, increased radiation, and soil with different compositions. Research in this area could help create hardier, more sustainable crops for Martian agriculture. Algae cultivation. Algae are rich in nutrients and can be cultivated in bioreactors. They can serve as a source of both food and oxygen. Algae-based systems could be integrated into the life support systems to enhance sustainability. Successfully creating a self-sustaining food supply on Mars would likely involve a combination of these methods, adapting and refining them through continuous experimentation and research. It would also require a comprehensive understanding of the Martian environment and the nutritional needs of the astronauts living there. Water supplies on another world. Creating a sustainable water supply for astronauts on another planet would be a critical aspect of future manned missions to other worlds. There are proven scientific methods for obtaining water on other planetary bodies. Extracting water from the soil. If another planet has significant amounts of water ice in its soil, especially near the polar ice caps, this would be possible. Scientists and engineers are exploring techniques to extract water from regolith materials. This could involve heating the soil to release water vapor, which can then be condensed and collected. Importing water. Water could be transported from Earth or obtained from asteroids. This would be an expensive option and is less desirable for long-term sustainability, but it could be an initial solution until local resources can be fully utilized. Harvesting atmospheric water. Even planets with thin atmospheres may contain some water vapor. Devices could be designed to extract and condense this water from the atmosphere This method might be challenging if the planet has low atmospheric pressure. Melting ice caps. Planetary polar ice caps can be composed of water and carbon dioxide. Heating these ice caps could release water, which could then be collected. This method, however, has environmental and ethical considerations, as it might impact the natural ecological environment of the planet and would need to be strongly researched first before being considered. However, if it's identified safe to perform, this method could provide abundant supplies of water to the space colony. Recycling and filtration. Efficient water recycling systems will be crucial. Astronauts would need to reuse water from various sources, including urine and humidity in the habitat. Advanced filtration and purification systems would be essential to ensure the water meets the required standards for consumption. Bioregenerative life support systems. Plants can play a role in recycling air and water. Bioregenerative life support systems involve growing plants that absorb carbon dioxide and release oxygen while also contributing to water purification through transpiration. Solar desalination. Solar-powered desalination units could be used to extract salt from briny water sources if available on another world, making it suitable for consumption. This method requires a stable energy source, and the availability of briny water needs to be confirmed. It's likely that a combination of these methods will be used to ensure a stable and sustainable water supply for future space colony establishments. Developing and testing these technologies will be crucial before sending astronauts on long-duration missions to the another world. The role of artificial intelligence. Artificial intelligence is integral to the success of space colonies. AI systems can manage and optimize life support systems, monitor environmental conditions, and assist in decision-making processes. Human-machine collaboration is crucial for overcoming the complexities of space colonization, as AI can handle routine tasks, freeing humans to focus on more complex challenges. Pioneering the future. The dream of establishing a colony in space represents the culmination of human imagination, scientific progress, and technological innovation. By venturing beyond the confines of Earth, we open the door to a future where humanity thrives in diverse environments, pushing the boundaries of what we once thought possible. The establishment of a space colony is not just a scientific or engineering feat. It is a testament to the human spirit's indomitable will to explore, adapt, and overcome challenges. As we pioneer the future of space colonization, we carry with us the collective dreams of generations past, present, and future, a testament to our boundless curiosity and the unwavering belief that our destiny lies among the stars.